Thank you for attending my talk. My name is Xi. I'm a PhD student from the UNC Chapel Hill. I'm very happy to present our work, the acoustic foveation. This is the first approach in introducing the foveation into the acoustic rendering. As a VR researcher, I think foveation is a concept that is familiar to everyone in our field. Specifically, it refers to the phenomenon that our visual sensitivity is at its peak in the foveal region. However, as the eccentricity is going up, our visual cue will tend to be less sensitive. And at a higher peripheral area, our visual acuity will be significantly diminished. As a result, the visual quality of objects in this area becomes largely imperceptible. This phenomenon in our human visual system inspired the foveated rendering, a key technology in advancing the VR experiences by balancing the high visual quality with the efficient resources usage. It leads to more immersive and more responsive virtual environments. By reducing the rendering workload in the areas that the user is less likely to notice in detail, foveated rendering can significantly lower the computational load. This technology has also been widely used in the live field display and also in the holographic display. By considering the other perceptual factors, the foveated rendering can also incorporate the effect of the high-level cognitive processing. Motivated by this promising approach, we pose two questions. How about the audio rendering? And can we implement the concept of the foveation into the audio rendering? In order to answer these questions, let's first take a look at the problem in the audio processing pipeline. The computational requirement of the sound propagation algorithm increases linearly with the number of the audio sources. Especially in the dynamic scene with a large amount of the audio sources, the computational load can quickly become overwhelming. It makes the real-time audio processing a significant challenge. So why don't we reduce the number of audio sources? If we can cluster the audio sources that are imperceptible to the users, we can reduce the computational load in the audio processing pipeline. To this end, we want to explore in which area the user becomes less sensitive to discriminated spatial audio. This area provides us the region where the cluster audio is not perceivable by the users. Therefore, we want to know the minimum threshold without compromising listeners' perception of the spatial audio. And this is known as the minimum audible angle. It is a concept that represents our sensitivity to the spatial audio localization. Similar to the foveation in the human visual system, that the visual sensitivity is dependent of the eccentricity. The minimum audible angle is also dependent of our azimuthal eccentricity. So we aim to achieve the acoustic foveation by systematically exploiting the fall-off in our audio spatial acuity along with the azimuth. With this aim, we conduct a user study. Given a specific azimuthal eccentricity, the participants received an audio event with an angular offset by this azimuth. Another audio event with the opposite angular offset will follow by a small delay. Participants were asked to report whether the second audio was to the left or to the right of the first audio. Based on the user's response, the program will automatically adjust the angular offset. And this procedure is followed by a 2IFC staircase. The staircase increases the offset after an incorrect response and decreases it after consecutive correct responses. It determines our perceptual threshold of the angular offset and therefore measures the minimum audible angle. This procedure evaluates our audio sensitivity in each azimuthal eccentricity. Considering the massive number of the sound events may occur concurrently, we also validate the masking effect of the background audio in our acoustic perception by inserting different amplitude of the noise. The results confirms our hypothesis. The azimuthal eccentricity largely changes the spatial audio perception given the direction, and the background noise doesn't significantly affect our spatial audio localization sensitivity. Inspired by the discovery, we fit a generalizable model to predict our audio localization sensitivity. In order to establish a robust model with the individual variances, we include a percentile index in our model. A lower percentile corresponds to a more conservative discrimination threshold prediction. Guided by our model, we developed a perceptual sound source clustering algorithm. Specifically, the algorithm progressively clusters the audio sources within their minimum audible angle along with the azimuth. For the future application, we evaluated our algorithm in VR. The participants listened to the cat and dog sound rendered in an indoor scene, and the angular distance between the two sound sources were placed with our model's minimum audible angle prediction. The audio events in our study were simulated with unclustered condition, and also in the clustered condition. Participants were asked to determine which audio event was unclustered. Based on our results, the clustered audio event only requires half of the computational demand of the unclustered audio. However, the participants were unable to distinguish between the unclustered auditory space and conservative clustering audio. This observation reveals that our clustering algorithm can reduce the computational time by 50% without compromising the audio perception. We also measure the method's performance with a large-scale audio source clustering simulation as a pressure test. The assessment shows that our algorithm is able to achieve 94% of the time-saved ratio and reduce the 300 audio sources to 15 sources. In conclusion, we achieved the acoustic foveation with a large-scale perceptual experiment and the perceptual-guided audio clustering algorithm. We hope this work will inspire new frontiers in perceptual graphic beyond division. For example, we can incorporate the attention awareness in the acoustic foveation, and we can also considering the multi-order audio. Thank you everyone, I hope you enjoy my talk.